There. Sweet. All right, today we're going to be taking a look at doing some simulations in Solidworks. If you haven't already done so, please go ahead and open up Solidworks. And then if you come to our course page, and then scroll down to our week 3, which I just published this morning, and then download this roboarm.sldprt. And then we're going to open that up in SolidWorks. Just waiting for that to finish loading.
Duo was slow to call.
What's that?
Duo was slower to call.
Yeah, you gotta get authenticated, get into Apps Anywhere, you gotta get into Canvas. It always takes time to get all that stuff going. I mean, I'll talk a little bit about what the plan is here. So while you guys are getting that loaded in, you know, we can discuss the kind of the objective for today. So this is a link intended to be used in a robotic arm. It's got 2 mounting points for NEMA stepper motors. So that way you can control the position of it. It's about a ½ meter long. The sidewalls here are currently 5 millimeters, and then it has a hollow tube for the primary length of the part. Take a look at that real quick. There we go. That tube is, I think, 2 or 2.5 millimeters thick currently. With the idea that you could fabricate this using some aluminum plates as well as an aluminum tube, so the cost of construction would be relatively minimal. The complexity of construction is also kind of relatively minimal. So that's kind of the thought there. And this didn't specify a material, so I'm gonna go ahead and edit material. And I'll give it like a 6061 aluminum or something that's a nice kind of standard aluminum alloy. Easy to manufacture kind of thing. We do need to have a material that has strength characteristics included in it to be able to do our simulation. So make sure you have, if you want to use different material, that's fine, but make sure you got an elastic modulus, make sure you got tensile strength. Make sure you have a Young's modulus, which is, I guess it's the same as elastic modulus. So what we're going to do is I'm going to assume that this thing is primarily held in place by these screws that mount to the motors. And then I'm going to apply some loads and some torques to one side of this and then kind of see how that responds. But my goal is to look at the distribution of stress as well as the directions of the stress. So when we looked at doing FEA analysis prior to this, one of the primary things we looked at was just what's called the octahedral stress or the magnitude of the stress. And I want to show you guys you have tools to look at not just the magnitude, but also the direction of the stress, and then get a little more details as to kind of where those stress concentrations are, what the directions are, and things like that. So hopefully that makes sense, and we'll have enough time to look at all those different things. Anyone besides Christiana still waiting for their part to load? All right. So anyone have any questions about that while we're still kind of getting a few people set up before we go into actually running the study?
Yeah, when you do the edited material
feature,
after you select it, will the edit material feature close out or will it stay open?
So if after I hit apply,
Yeah.
it will stay open. I have to hit close to close this,
Okay.
but it will apply the material when I hit apply. So if I hit edit material and then hit close,
Okay.
it's not going to edit it and not going to apply it unless I actually hit apply. So you want to go edit material, find the material you want, hit apply, and then hit close.
Yeah, I wanted to make sure it
wasn't like an error. Yeah,
Okay.
that's just the way it's set up. It would make sense to have, like an apply and close button or something, but I think, yeah, but it works fine.
Okay.
And if you can always customize this smart menu too. There's kind of like manage favorites. So if you have a certain set of materials that you're using a lot, that's not this kind of default list, then you might want to do that, just so that way you can say, click, accept a lot faster. Any other questions?
This is the file we put under week 3.
Yes, this is a file under week 3. It's just a SolidWorks part file. What's that? You have SolidWorks. Your default program to open the file is probably wrong. Just open it from SolidWorks. Software version. Also, Christiana, you might want to go ahead and get logged on. I don't know if you're using the student design kit version, you're not going to have access to the full simulation toolkit. So if you're trying to do this from home, you're going to probably have to do it through the apps anywhere. At least that's been the case in previous years. SolidWorks always changed what is included in that student design kit. So there's some potential for revision there. All right, let's go ahead and start looking at our simulation. If you don't have the simulation tab, and you want to turn that on, I'm going to go into the SolidWorks add-ins and make sure I have the SolidWorks simulation selected. That's going to turn on our ability to run the simulation tool. If you don't have the full simulation kit, you can run Simulation Express in the Evaluate tab, but that's going to give you a lot less options, and most of the options we're looking at today are not going to be included in that. So we do want to make sure you have simulation on, go into simulation, and we are going to do a new study, and we're just going to do a static study. The vast majority of the stuff that I do on a regular basis is still just static simulations. You do have these other options. We're going to be looking at some thermal and some flow analysis studies in a later lecture in this course. But for now, we're just going to look at some of the details we can get out of these static studies. So, and you can call it whatever you want. I'm just going to leave it static 1. Now we have our material in a mesh, our connections, our fixtures, our external loads, the actual mesh results, and then whatever simulation results that we want on here. Because we haven't run a simulation yet, we don't have any results there. I'm going to start off with a very simple set of constraints. I am going to fix the 4 holes on the proximal end. So I'm going to do fixed. Oh, wait, I don't want to use the advisor. I'm clicking the wrong button. You can use the advisor if you want. I just don't want to. I just want to add a fixed geometry to these 4 holes. The fixed geometry is the simplest contact that you can do to fix a part relative to the assembly or the part coordinate system. That's just going to prevent any motion at those surfaces. And really any motion at those elements that are going to be on those surfaces after we mesh the part. Right.
You click inside the hole.
Yeah, so I clicked on the face inside the hole. And to be clear, I am getting the faces on there. Why do I have a fixed hinge? I actually have them all as fixed hinges as opposed to fixed geometry, which I guess is fine. But you can just change these options here. If I do roller slider, it's going to allow it to translate along that, which I don't really want. Having a fixed hinge is actually probably a slightly better constraint on this one because those screws are really not going to prevent rotation, right? So treating them as a pin is probably a pretty good idea. So actually, I'm fine with that. I think I'll leave it like that. Should work good. And I can replace those with connections and do like bolts and actual bolts and pins to get an even more accurate approximation of the failure points. I wouldn't suggest starting with that. So the first thing that is kind of the common consideration in a simulation analysis is that you want to figure out where your stresses are highest first. and then worry about the accuracy of the simulation in those areas of concern, right? So unless I see that those bolt holes are like high areas of stress concentration, I'm not going to really worry about that being the failure point. And if I'm not worried about that being the failure point, I don't really care what the bolt constraints are. As soon as I am any kind of reasonable distance away from that constraint, the type of constraint isn't really going to matter as much anymore, unless it's really allowing for motion or not allowing for motion in a direction that it should be moving, right? So I'm fine with that for now. And then I'm going to start off just by applying some simple loads onto the end of the arm here. So I'm going to go and apply the loads again to these bolts, but I'm going to do it in specific directions. So we're going to apply, let's do two different loads. I'm going to do a force. And then I'm going to apply them to the same surfaces. But rather than applying them in a normal direction, because I'm not trying to make these holes get bigger, right? I'm not trying to pressurize them out. I want them to go in a specific direction. And I'm just going to use the kind of opposite face of this for the direction of the force. And then I need to come down here and tell Solidworks, okay, what do you want the direction to be relative to that face that I selected? So I said that, hey, I want to use this face as the kind of the direction of my force, but do you want it to be normal to that face along the x-axis or the y-axis of that face? What do you want? Also, do you want to have that force applied as 1 per item, which means that it's going to be 4 times for the total force, or do you want it to be the total force? I actually want it to be the total force, right? And I'm going to do 2 different directions. I'm going to do normal to the plane, and let's do 100 newtons. Then I'll do along the plane in the first direction. And let's make that, I don't know, let's do it 200 newtons. And you can actually see those different forces, right? So there's the one that's kind of along the plane there coming out the side, and the one normal to the plane kind of going towards the plane. Does that make sense to everybody? One thing is that sometimes inside the simulation kit, and this is just like a bug, you'll type the values into there, but it won't actually accept them. So after you've got that all set up, I really suggest you look at the values and you go back and you kind of edit the definition on your force and make sure that it kept the values you typed in. Does that make sense to everybody? Sometimes you'll type in a value and then you'll hit accept and it won't have actually changed. It'll still be whatever it was before you typed in the value. So just check and make sure you're getting the results that you want. Also in simulations, usually a good idea to start with, I guess what would be a non-conservative load, a lower load, and then work to higher loads once you know the simulation is going to run appropriately. Because the larger the load, the more likely you are to have some kind of error when you are running the simulation. Does that make sense? All right, so let's run this and see what happens. If you get an error, just share that with the class and let me know what the error was and we'll take a look at it. Prashana, if you haven't applied your material, we're using 6061 aluminum. So make sure you have that considered. So as you can see on here, I do have those higher stress concentrations at my mounting holes. So it seems like that's going to be an area of concern for my design. And then as I go down, really I'm seeing a lot less stress throughout the entire part, right? The easiest way to resolve that would be to look and see, okay, well, I can make that base plate thicker, right, to better distribute the forces throughout that. And I also might want to go back and look and see, you know, how could I make this portion here a little bit more accurate, so that way I'm getting a better idea of what the stresses actually are inside that portion of the part. I want to, for now, actually kind of ignore that result and look and see if I'm trying to design different aspects of this, maybe I don't care about the stress in that specific area. And I want to try and see where the stresses are in the rest of the part. You'll notice that my yield strength here is this kind of blue area. And because I have this stress concentration at my hole mounting spots, and specifically really just kind of like the ones on the one side, right? I'm not able to see what the distribution of stress is in the other portions of my model, right? So if I want to see what the stress distributions are in my model, what I really want to do is I want to change the scaling on this stress plot, right? That's the first thing we're going to look at. So I'm going to look and see, okay, say I'm going to ignore that base plate, right? That's not a significant portion of the overall mass. You know, I've used some washers or whatever to help distribute the force on that face. You know, that's not my concern in the design right now. So I want to ignore that and move on to something else. So I'm going to change my stress plot to look and see to get a better idea of what it looks like for the rest of the part. So I'm going to go here to the chart options. I'm going to right click on stress one. Did anyone not get us a result in the simulation? I see Chrisana doesn't have a result. Did you apply material, Chrisana? So if you have the simulation open, you can apply it, right click on the purple arm here. No, just do edit and then give it. Anybody else not having their simulation result? All right. So again, I'm going to right click on the stress plot. I'm going to go into chart options. And then I have a lot of options in here that I can use to change how this displays, right? And right now, my maximum defined value is based off of the maximum stresses that I have observed inside this part. Well, if I want to see, you know, kind of the distribution of stress relative to the maximum strength of the part itself, then maybe I want to change this off of that value, right? And you can see here that my maximum is 5.5 times 10 to the 7. So I could do 5, 5, 5, 5, and then 6 more zeros. 1, 2, 3, 4, 5, 6. I think that's right. 1, 2, 3, 4, 5, 6. I can't see it, but I'll know. Yeah, that's 6 zeros. So 55 megapascals. And I could change the units on here so I wouldn't have to use the 0.00000, because right now it's in pascals. If I change it to newtons per millimeter, I could use megapascals instead, right? And if I accept that, did I type in one too many zeros? I think so, yeah. I want to have 7. 1, 2, 3, 4, 5, 6, 7. Okay. Now I can see what this stress distribution looks like across my entire part, right? And you can see I have some areas of higher stress over here. And obviously, as I go down to my distal portion, I have a lot less stresses because, again, if I'm applying these, really what I'm doing is I am applying a moment across this whole thing. But let's say this is probably, maybe this is fine, right? As this portion of the assembly, but I'm gonna say, wait a second, really what I'm gonna have is I'm gonna have a force further out on this product, right? Like further down the line. And so not only is there going to be forces applied at that endpoint, but there's also gonna be some kind of torque applied by, that motor connecting to the next piece down the line, right? So the next thing I'm gonna add is I'm gonna go back and I'm gonna add a torque to, again, that entire face, just like we did before, but centered around the central axis of the part. So I'm going to go back into my loads, right? And then the second option I have here is torque. Everybody see that? And again, you'll notice that as I do that, it kind of hides my results. I'm going to apply those to the same faces. So again, I'm just going to assume that my circles here are continue to carry the torque. And then the face I want to use for the axis of the torque is going to be this central hole. So this is still the distal end of my robot, the same one I was applying the forces to before. And that's generally kind of a good idea, right? You generally want to have one side of your simulation being fixed, and then the other side being the one where the loads are being applied. You don't want to mix those and have like, I'm going to apply some fixtures and loads to one side and some fixtures and loads to the other side, unless your assembly is such that that's really realistic for some reason. Yeah.
You're replacing the forces with torques.
No, I'm just adding a torque to the end of the robot. I'll add it. I'll just start over. I mean, not all the way over, but I'll go back to the torque definition, right? So I went to external loads. I'm not editing the force. I'm just doing external loads torque. That's adding a new load to my system. And again, I'm using the cylindrical faces of my mounting holes as the faces to apply the torque to. But then for the direction of the torque, I'm using this central hole. You'll notice that what that's doing is it's making all of the forces kind of go around that central hole. In fact, if I kind of highlight over there, you can see that force field, I'm going to call it that, a little bit more evenly inside that, in that port there, right? And I'm going to make this 300 Newton meters. So a pretty big torque, right? Keep in mind that we just applied a 100 and 200 newtons of force across the distance of a half a meter, right? So we were producing something that's kind of a similar magnitude to this, but this is a larger torque than is being generated by those other forces that we applied. Does that make sense to everybody? To some extent? Okay. Cool. All right. So I'm going to accept that. And then I'm going to rerun my study. Again, this is going to generate a new results plot. And you can see with that torque, now my whole thing is failing. I still have the same maximum on my stress plot as I did before. So that's probably a little too high. Let's go to something a little bit less. That way we can see this a little bit more discreetly. I'm going to edit my torque. I'm just going to bring it down by a factor of 10. Let's go to 30 Newton meters. That's a little closer to the same force we were already applying. We didn't take those other forces off, right? So we're compounding these. That looked a little bit better, right? And now we can see that we actually have, again, a little bit more kind of realistic thing here as to what our forces are looking like. We still have that high concentration of force down by our pins. So that's something we would have to adjust in the design at some point. But if this is force is what we're expecting, that's probably a little bit closer to an appropriate force for kind of the size of the tubing that we have. So, that making sense so far, everybody? All right. So now what I want to do is, okay, well, if that's the forces in here, how do I look at the directions of the forces, right? How do I figure out how much force is actually being applied? The first thing I'm going to do is I'm going to define a new stress plot because I don't want to have to redefine my plots every time. I want to be able to toggle between them, right? And I can get whatever new plots I want from this results option if I right click on results, and then there's all these different types of plots, right? So factor of safety, displacement, strain, and you can customize each of these however you want. So what I'm going to do is I'm going to make a stress plot storing the stress in the, I think it's the X direction, the direction along the length of the part, right? And then I'm also going to make it so the deformation scale is 0, so that way I can see the locations of those a little bit more easily. Because right now the deformation scale is like 500. So right click on results, click on define stress plot. I'm going to use a user defined deformed shape as 1, right? I also do true scale, it's the same thing. on here, the von Mises stress, right? That's a form of octahedral stress. It's basically, that's going to be the root sum of squares of the stresses in the X, Y, and Z direction. It's a little more complicated than that because it's actually, I think it's the square of the stress in the X and Y direction plus 1/2 the shear in each of the X and Y directions squared. But it's basically, it's the magnitude of the stress, right? Which if you have a isotropic material, right, that's the same properties in all directions, then that's probably fine. But if you have an anisotropic material, or you care from a design standpoint how the stress is being distributed, you probably want to look at, you know, the actual directions of the stress. So here we have our X normal, Y normal, Z normal, as well as our shear in the X, Y, X, Z, Y, Z planes. I said before that I wanted to look at the X normal stress, the stress in the X direction along the length of the part. So I'm gonna click on that one. Again, I can change my units if I want. So I talk about using megapascals instead of pascals. And if we want to, we can also say, hey, if you want to specify a direction or a coordinate system, you can do that. I think if you leave that blank, it should just use the coordinate system of the part. But if you want to define a different direction, like say you want to find the stresses in, you know, a 45-degree angle from some plane or something like that, you can always do that instead of just using the default, right? And I should be able to click on OK and create that plot. There we go. And we can see here that that plot gives us a fairly uniform distribution of stress. So the stresses in the X direction, the negative range on this is all messed up. So we need to really change the options on this. I'm gonna go to my chart options. I don't know why it's at the minimum value to -80. I'm gonna adjust that to 0. And I want to put my maximum value back to that 55. Now, this is a little bit deceiving because you could have a situation where you have negative stresses, you know, compressions instead of tensions. I don't think I have any tension inside this part. Probably have a little bit. Actually, let's exaggerate this and see what it looks like. So look at my chart options. I'm actually going to use -5, and we'll do +5 as my values. So if I really care about what areas of the part are in tension versus compression, the problem I had before is that my ranges were too huge, right? So everything was green. I wasn't seeing what the distribution of stresses are. If I lower these ones, this is showing me which regions of the part are in tension, which is shown in red, and which of the areas of the part are in compression, shown in X, just in the X direction, right? So normal to that. And you can see that because I'm applying this moment kind of at the end going in this direction, the surfaces on the right side of the part are in tension, and the surfaces on the left side of the part are in compression. And it changes a little bit as you go from having that distal portion being the driving force down to having those distal forces that are being applied driving the moments inside the part, right? And so again, to accentuate that, changing these values can be helpful. Maybe I want to use +55, -55. That's going to show me which ones are closer to their maximums. But again, depends on what you're trying to do, right? Are you trying to understand what the distribution of stress looks like, or just where the failures occur? If you just care where the failures occur, then you probably are just using those octahedral stresses anyways, right? But if you want to know what the distribution of stresses look like, then you're going to want to look at these more advanced options to understand where the stresses are occurring. I could also go back and make the loads bigger to make these stresses higher. For now, I'm just going to make this, I'm going to make this like 20 to 20. So I have a better idea of what the distribution looks like, but it's not so Boolean, right? That's probably just because I'm making up numbers as we're going. I just want to see some color gradation through this part, right? So I'm picking values that are going to give me some distributions of stresses inside this assembly, right? So again, if I look at this, I can kind of see in this direction, I have high stress concentrations here at the neck, right? Also at the base. Then I kind of have some neutral axes here. And then one of the things I might want to do is I could suppress these different forces and then rerun the analysis and see how that changes my results, right? So I can always go back and suppress my force, run the study, get a new result plot. And then I could always save and export these results relative to each other to kind of figure out what's driving the stresses inside my part, right? And I don't have to do just the X direction. I can define more plots. So I can go back and I can say define new factor of, or new stress plot, right? I can use my true scale. Say we want to look at the Z direction now. I'm going to go ahead and change my chart options right now to make it consistent with the other one I have. So I'm going to use, I wanted to change my unit system to megapascals. And then I can go from 20 to -20. One thing that I would suggest is try and use the same chart options regardless of what directions you're looking at. If you are doing an analysis, can I make this flatter? There you go. I can zoom in a little better. If you're doing an analysis, looking at multiple directions like this, so this is the X direction, and you see there's a lot of variance and stress on this scale and the X direction. We go to the Z direction, because there's not a whole lot of distance in the Z, and so the variation in forces along the main portion of the shaft is not really changing, and the stresses are pretty close to zero in the Z direction, with the exception of at these end plates, right? But you want to keep these scales consistent, because otherwise, if I have a report like this, right, and I have this picture, and then next to it I have this picture, the person reading that report is going to think, oh man, the stress has got so much higher, right? Because unconsciously, they're going to think that those are the same scales. Now, if they're smart, they'll probably go, oh, the scales are different. Okay, I get it now. That's why they're not actually higher. They're just showing me it from a different perspective, and therefore I get different values. But again, the first reaction there is going to think like, oh my goodness, what happened there? Why are the stresses so much higher in the X direction than they were in the octahedral stresses? Because they shouldn't be, right? Like the maximums on this sail should still be less than the maximums on the octahedrals, right? Because I can't have a component of the stress be larger than the magnitude of the stress, right? So you got to think about those kinds of things. Does that make sense, everybody? Anyone have any questions on kind of diving a little deeper into the stress results, just from the standpoint of showing different, directions of stresses and creating new plots? Right. The other thing we might want to do is we might actually want to see the stresses inside the parts. And so if you want to see the stress inside a part, you're not inside an assembly where you need to just hide a part. You can always hide and show different components, right? But you might want to see what the stresses inside the geometry of a complicated part are. We can take sections of the stress plots and then show those, right? So inside this results options, you see there is, it's inside the chart options. I'm gonna go to my X one. There's an option to do section and then ISO clipping. The ISO clipping, we'll do each of these, but the section one basically lets me say, hey, cut the part in half and show me the stresses on this cut, right? The ISO clipping allows me to say, hey, show me all of the regions of the part that have a stress that is more than whatever this cutoff is, basically hiding the parts that are lower than that. And sometimes that's nice because it'll show you, like, you can hide all of the little bits that you don't care about and see into the inside of the part, right? So let's look at each of those in turn. We'll start off with section clipping. I'm doing this on a part with a zero deformation scale, right? Oh no, I have a true scale deformation, sorry. Before I do this, I'm gonna right click on my chart options. I'm gonna go to my definitions. I'm going to do a user-defined scaling of 0. The reason I'm doing that is because when I do my section cuts, I want to use the original geometry of the part, not the deformed geometry. And I'm doing that because I want my cuts to not curve as it's going through the part. Does that make sense? So again, if you have that, go into your chart options, the definition, change your user defined scale to 0. And now the geometry of the results is exactly the same as the geometry of the initial part. Then I can go into my chart or to my section clipping. And now I can go halfway through the part, which I think should be 35 millimeters. I think it's 70 millimeters tall. I'm just going to type in 35. Then I can accept that. And now I have the stress distribution inside the part, right? And this works almost exactly like the section view tool inside the kind of regular model views. So you can change this to be, relative to different planes and stuff like that. So if I change this from the front plane to the right plane, right, I can look at that. Or if I wanted to look at just a cross section of the tube, look at that. And again, you might really care about this weld point, right? Like if I want to see how this weld is distributing that stress, and maybe I want to get right kind of into that point there and see what that stress distribution looks like, which is pretty helpful. You can also have these different options for doing like spherical and cylindrical offsets. Those are hard for me to think about from a practical standpoint, right? Like here I'm doing a cylindrical cut out of this face. I don't find that to be especially useful, but I'm sure someone thinks that they're helpful. Same thing for the spherical, like, I don't want to see the stresses on a spherical plane, but you have those options. And you can also do intersections, so you can go for kind of multiple cross points to get more detail on where those stresses are. I've never been in a situation where I was not able to see the stresses inside of a part just using straight cuts, right? Like I don't have parts that are that complicated, I guess. Maybe for like a gear or something and you wanted to see the stress at the base layer of all the gears or something, you'd use a cylinder. I don't know. I think I would still just look at one tooth and assume that they were all consistent. We usually only have one tooth in contact with it at a time anyway. So I can't think of a situation where that's helpful, but they exist. Someone I'm sure knows. Does that make sense? Anyone have questions about doing these section cuts? Again, almost exactly the same as using the section tool in the model view options, except for we're seeing the results being cut. And just to be clear, if I try and use section views inside the simulation, it doesn't do anything, right? Section view is now on, but it's doing the section view in the model, not in the results, right? So when you show the results, it's really showing you, it's hiding the part and showing you the output from the simulation instead of the part. Which is why you run a simulation on your computer, you have all of these files, you have a different file for every plot you're putting on here. So if you're making tons and tons of plots, you're gonna have even more files in those folders, which is not a problem. But if you wanna take those files with you as you're changing things around, you wanna make sure you're doing that, all right? All right, let's look at the other option here. I'm gonna go to my, let's go back to my external plot. I'll just go to ISO clipping instead of section clipping. And the ISO clipping is very straightforward. I specify the value and the direction that I'm clipping across, and it hides everything on the opposite side of that. So this is all the values that are above 12 Newton meters, all the values that are below 12 Newton meters. Keep in mind that we're doing this on the directional stress. So again, we're going to have negative stresses here. So I can actually go negative 20, right? And show you all the values that are less than negative 20. I think the range on this is defined as the range for the chart. So if you want to look at a higher cutoff, you need to change the range on your axes here. Does that make sense? On this one, if I look at all the values greater than 20, there's really not that much. Look at all the values less than -20, there's really not that much, right? This is a nice way of seeing inside the parts, because again, you get to see exactly where all those values are very clearly, right? And also, if you're colorblind, very helpful. Or you could just, for me, it's more like I can see color reasonably well, but it's easy for me to miss things where there's just small changes in color. So I might have missed the fact that we have kind of these smaller areas over here, right, that are above that value that we care about, right? It looks like you can also do clipping on the ISO, or just kind of turn it on and off as well. I've not done this, but apparently I can sandwich the values as well. So I can show all the values greater than a certain value and all the values less than a certain value. If I switch these, all the values between those two values. So again, the more you play with this, the more you're going to realize you have a lot of options as to what you can do with these things. I think one of the things that I would use this for on a more practical basis is that if I wanted to 3D print this part, I can see here that if I printed this flat, the stresses in the Y direction are not that large, right? So I'm not going to be as worried about this part kind of delaminating in this direction. If I printed it flat like that, the areas I would have to worry about this breaking are really just kind of these same endpoints I had before. So I can make these back walls and this base plate fairly thick and probably add some rounds to that and not really worry about this central diameter of this tube. And really for this whole thing, it's a lot bigger than it needs to be. So if these are the loads I need to stand, I probably want to go into my design, edit, say, the tube diameter, right? I can make this from 2.5 to 1 even, except that. And then go back into my static, rebuild, and rerun the study and see what that does to my stress distribution. Now, I should make it significantly higher inside my results, but I'm going to go back to my X normal, show that. Oh, I still have my ISO clipping off. I can just turn this off, right? And now we have, again, those much higher values inside there. Go back to my octahedrals, show those, right? Now we're exceeding our kind of our maximum stress there at that distal end. I must have set this up so that way my moments are actually counteracting each other. So the moment that I'm applying there, as well as the force that I'm applying as I get close towards the base, are actually canceling each other out. Which, if I'm assuming that the load can be applied in either direction, is probably a good thing to go back and say, okay, well, if the moments are canceling out in this direction based off the way the robot is operating, I probably want to go back and flip that around. Actually, I still have my forces hidden. I'm going to unsuppress my forces and try rerunning that. Yeah, so it still looks like they're canceling each other out, right? And go and edit the torque, flip the direction of that. I don't know why I can't. Oh, because I'm clipping the part. I couldn't tell if I was actually flipping it because I was clipping that. I don't think I did. Reverse direction. There we go. Now I think my forces and my moment are going in the same direction. Rerun the study. Right. And now you can see I have that concentration of forces at the base being higher than it is at the tip. So that's another thing you want to consider is if you have loads being applied in multiple directions, because that's the constraint of your simulation, you really want to test this situation where all the loads are being additive rather than canceling each other out as your conservative estimate. I would also be a little bit cautious about just doing just that, because you may find that the forces in specific directions get kind of funky with different combinations. So you probably want to test, some variation of all possible combinations. Not actually all possible combinations, but a subsampling of that, right? So 10% of all possible combinations sampled evenly across all possible load configurations, rather than just all of them in one area and not the other area, right? Or all of them in one direction, not in the other direction. Yeah, Fernando.
So I don't know if I can expect, but it's not like something on it.
Yeah, so if you go into the stress, you show it, then you go to ISO clipping, you can toggle it on and off with this button down here. I think you can do the same thing with the section clipping. If I make a section clipping that actually does anything, I should be able to toggle that section on and off. There you go. And that's helpful if you want to use like a standard section clipping and be able to just have it, there or not there, right? And all it's doing is saying, hey, don't visualize anything past this point, right? So it's not like it's computationally intensive to do that or not do that. That's all the things I really wanted to cover today. Anyone have any questions about stuff that we've covered previously or want to reinforce another topic? Yeah, Will.
To edit dimensions based off of your simulation results.
Yeah.
So like if, for example, this part is so long, right?
Right.
If you put a force on it, you want to only express a certain distance, like how long can the part be that distance?
Yeah.
That force, right?
Yeah, I mean, so I'd probably do that with an iterative analysis. If I say it's 10 inches long, right? And it displaced a tenth of an inch. And I only want it to displace, half of that. Then I'd try and make the second moment of area, right, twice as large, so it had a higher resistance to bending, which might be increasing the diameter probably by a quarter or something, right? Because if I double the diameter, I get 4 times the second moment of area, right? Because it's a square function. Or I make it just a little bit taller, but I don't make it any wider or something like that, right? If you want to have a displacement load, you can do that here with the prescribed displacement. And you can say, hey, I just wanted to go this far and then see what the forces are to get that distance. That's under the loads options. So if we go loads here, prescribed displacement, you can just say, hey, I want this to move that far. And it'll back calculate forces from the displacement as opposed to calculating the displacement from the force, right? That's another thing you can do to try and revise the design to get that better. Again, different options, depends on what the constraints are, right?
You can use them. Just like a design step for that.
You can do all of these things in a design study, right? So if we go down here to the bottom, there's the option to create a new design study. You can also do that through the new study, design study options. And then you got to decide, okay, what are the conditions, right, you want to optimize? We definitely don't have enough time to go through all of these, but you can add different things to here. Like, so let's say we add just the length of the rod, right? As the thing we're going to change. Parameter is not defined. And just give it a name. There we go. So the length of the rod, right? I can specify what kind of constraints do I want. So I could say that the simulation stress von Mises, right? Let's use megapascals, model max across all steps. And I say is less than, let's say, I think I'm already over 50. Let's say 100. Right? And you guys specify what study parameters you want to use. So right now I'm using static 1. But if you had multiple studies in your part, you could guide that with different studies. And then like I said, the goal is to, this is say minimize mass. Usually minimize mass is like the easiest thing to do, which is really going to make it shorter, which is not good because it'll just make it as short as it can. Let's say maximize mass. That'll make it as long as it can get. Because the only thing I'm changing is making it longer or shorter, right? So this will try and make it as long as I can while still having the maximum von Mises stress be less than 100 Newton meters, which I don't know if it is or not right now. But then you can run this and it's going to change that variable, or if you have multiple of them selected, the multiple variables, rerun the stress analysis, get whatever the stress is, do that again, and trying to figure out, is there a value if I try all these different values that is less than the stress criteria I specified, and also achieving the goal that I want. And it didn't work because my maximum stress was 152.7 megapascals, even in the shortest scenario, right? So, but again, you can define those however you want. I didn't think I'd have time to get through all that, honestly, especially not the whole simulation study. Usually it takes a long time to run because it's doing multiple iterations of the simulation. And simulations are notoriously kind of picky and error prone. So I was expecting at least some of you to have errors with your simulations that would slow this lecture down and have us not have time to finish, especially since all the previous lectures we've done in this class have basically rolled into your guys' next class. So thanks for coming, everybody. If you have questions you want to stick around, then I'll be glad to answer those. For those of you who are signed up for the 2 credit hour section, the first project, I guess, is being pushed back till next Friday. Then I don't know what we're gonna do with the second project, but we'll put it in there somewhere. Or maybe we'll get rid of that and just ignore it. Yeah.
Is there a weekly submission today?
There will be, yeah. I'll put it up right now.
Is it going to be just this file?
Yeah, just this file. Actually,
I stopped after like you started getting into questions.
Actually, I don't think I'm gonna do a weekly submission just because the simulation studies are really hard to submit.
Okay.
So we'll just skip that. I'll put a note on the thing saying, I'm assuming you did the weekly thing for today. Yes, the first project 1. Do you have it done already, Krishana?
Oh, I thought we did it today.
It was supposed to be due today, but since we didn't meet last week, Patrick had asked for an extension and I had said yes.
No, social club matters.